as the alternative. The third possibilities could be the central source in the form of intermediate mass black holes. The range of the mass could be of the order of, let's say, 1,000 to 10 to the power 5 solar mass. The problem was it was not detected so far of this range of masses for any astrophysical objects. But if we consider that these are the possibilities, then obviously at sub-Eddington limit, this kind of sources, the intermediate mass black hole sources, can produce this high luminosity that we really observe from these ultraluminous X-ray sources. Now, until these LIGO observations that recently they indicated that from the gravitational wave signal that at least 142 solar mass black hole is possible. So that is really encouraging, although it is an island to the domain of intermediate mass black holes, but there is a signature that the intermediate mass black holes, although it is just slightly above 100 solar mass, it's still possible. So with this, it is clear that all the possibilities that is being delineated in the literature, they are definitely are in contrast, and they are really inconclusive. So given that, if we consider that the ultraluminous sources, they are really accreting matter, then obviously we can utilize the properties of their spectral and the timing variabilities to study these sources. And if it is the possibilities, then obviously we can try to constrain the mass and spin of these sources just with the help of spectral and timing studies. And obviously that can be supported by the theoretical understanding. And obviously we will start with that. Okay, so this is a typical accretion process happening around the black hole XRBs. So let me see if I can find a laser pointer here. Okay, so this is the secondary, which is supplying matter to the primary, and the accretion disk that we are talking about, which is located very close to this region. And this is the accretion disk structure in the cylindrical geometry. The dark shade regions is the meridional construction of the accretion disk, and the light shade region is the top surface of the accretion disk. Now, with this accretion geometry, and obviously black hole is sitting somewhere here, the typical length scale of the accretion disk can be considered to, let's say, 10 to the power 4 Schwarzschild radius or something. So we consider an accretion disk model where the flow is relativistic, the viscous effect is considered, and the black hole is considered to be rotating, because this is the most generalistic way that we can study the black hole. And obviously all the active radiative cooling processes, for example, Bremsstrahlung, synchrotron, Comptonization process, they are present. So we consider all of their effects. And to relate the thermodynamical quantities like pressure, densities, and internal energy, we use the relativistic equation of state to study the black hole sources. Now, obviously, once we talk about the black hole sources, it's really important to study them in general relativistic scenario. But obviously, with this complex accretion disk geometry, it's really very difficult to study all those things in the general relativistic concept. So we adopt a very useful and practical tool, which is called the pseudo-Newtonian theories. And based on these, we write down the equations. I'm not going into the details of these equations. I mean, if it is really needed, I will explain it in the discussion time. But these are the conserved equations that one should take care while studying the accretion physics. The radial momentum equations, continuity equations, azimuthal momentum equations, and the energy equations. So these are the terms takes care of the heating and cooling. The interesting thing is the gravity, the space-time effect is considered here with this term. And recently we have developed a potential which mimics the space-time geometry around a rotating black hole very accurately, very accurately. And this is the potential described in the equatorial plane. With this framework, we study the accretion solution that that includes shocks. And I believe in some of the talks, the shock has been described in details. So, but in any case, I'm giving a very brief flashlight of the shock physics. So essentially, shock happens when the centrifugal force is strong enough to support the gravitational force. And once these two forces are comparable to each other at certain regions, so flow is halted and they are being accumulated, and they end up with a shock transition, and the accretion disk structure looks like something like this. It is something like that. Okay. So obviously, from the thermodynamical point of view, shock solutions are preferred. I'm not sure whether this movie will work or not. Anyway, it's working very good. So you can see that. I don't know how to stop it for at some point, but in any case, let's do it. So you can see that the flow from the outer edge means about 1000 Schwarzschild radius. If it starts accreting, it first passes through the outer critical point, make a discontinuous transition. Again, it passes through the inner critical point and goes into the black hole. So this is the Mach number plot. And what is interesting here, you see, flow could have entered into the black hole completely through this trajectory, but it didn't choose it just because if it has a possibility to go through this path, it can have more entropy than this one. So as you know that from the thermodynamical point of view, the higher entropy solutions is preferred over other solutions. So shock solutions are really important, and it is more likely than the shock-free solutions if there is a possibility of shock transition. So with these considerations, we studied the shock solutions and the other properties, other thermodynamical properties of the accretion flow. So here we show the Mach number variation in this plane, and the similar solutions I have just shown in the earlier slide. The corresponding velocity profile you can see here, and this is the density profile, and this is the temperature profile. These are the quantities are required to calculate certain observables that can be verified from the observational point of view. So that's why we are showing it. Now you can see in the after the shock, because in this region the density is enhanced, temperature is enhanced, and as I showed in the earlier slide, that because of the shock, the inner part of the disk becomes puffed up, and this region we call as the post-shock region. Okay. Now, if we consider the resonance oscillations, which is basically when the cooling time scales is matches with the infall time scale. Infall time scale means if you send a parcel of matter from certain region and allow it to fall into the black hole, the minimum time it takes for this, it's called the infall time scale. When this infall time scale matches with the cooling time scale, it gives a kind of modulation of the inner part of the disk. And if you quantify the frequency of this modulation, this is the way you can calculate. And this, and once you know this, then you can estimate that what would be the oscillation frequency that is associated with the quasi-periodic oscillation frequency that we commonly see from the black hole X-ray binary sources. And at the same time, we can also calculate the disk luminosity by computing the amount of energy loss from the entire disk. So from the theoretical point of view, these two quantities we can immediately calculate just by knowing the post-shock velocities and the other quantities like emissivity due to cooling, redshift factors, and the disk geometries. Now, for these particular solutions, which is calculated for a black hole of spin 0.99, which is extremely rotating black hole, and here we consider the accretion rate is 0.5 Eddington rate, and the viscosity is 0.01. So the quasi-periodic oscillation frequency and the luminosity is calculated for these solutions, which are here in terms of the black hole mass. So once you fix the black hole mass, so it will be scaled accordingly, both luminosity and quasi-periodic oscillations. This is calculated from the theoretical point of view. Now, With this expression, what we did, we vary the accretion rate, and for a fixed black hole spin and certain energies, you can see that the quasi-periodic oscillation frequency can ranges for a wide range, and also the luminosity can be ranges for a wide range. So from the theoretical domain, we have a lot of possibilities to explain the quasi-periodic oscillation, a particular quasi-periodic oscillation frequency and the particular luminosity, just by tuning the model parameters. Luminous X-ray source, and if you know its quasi-periodic oscillation frequency and its luminosity, then by tuning the flow parameters or the model parameters, you can estimate what would be the range of these parameters that gives this particular frequency and the luminosity for a particular ultraluminous X-ray source. Exactly these things we have done here. So to validate our model, we have chosen a particular ultraluminous X-ray source, which is IC342X1. Fortunately, this particular source exhibits a quasi-periodic oscillation feature along with this spectral behavior. So in ultraluminous X-ray sources, quasi-periodic oscillation features are not very common. Common in the sense, observationally, it is not often seen. But for this particular source, it do exhibit these features. And we took the observation for 11th August 2012 from XMM Newton and Newstar. And we analyze the timing properties and the spectral properties, and you can see the nights you can see a beautiful peak in the power density spectrum, and these are the spectral parameters and timing parameters we extracted for this source from these observations. So most importantly, you can have noticed that the quasi-periodic oscillation frequency that we get from this observation is something about 645 millihertz, and the luminosity is something about 7.6 into 10 to the power 39 arcs per second. So these two observational information we try to explain using our theoretical model for this source. So what we did, from the theoretical point of view, we have several parameters. In this case, what I tried to understand that if we fix the accretion rate for this source, something like about 0.2 Eddington rate, and the black hole spin is 0.99, then for a different viscosity range, you can see what range of energy and angular momentum can produce this luminosity and this frequency. So this color indicates the range of black hole mass. So this figure gives us an idea what would be the possible range for mass, energy, and viscosity, which can produce certain luminosities. But from the observation point of view, it's not possible to constrain the energy, angular momentum, and viscosity. What is possible to estimate? The mass, accretion rate, and the spin. So in the alternative plot, what we try to understand that if we make the energy and angular momentum of the flow freely, obviously we cannot make all parameters freely, that's why we put the viscosity fixed. Then if we change the accretion rate of the flow, and if we change the black hole spin as well, for example, black hole spin, once it goes to 0, it's a Schwarzschild black hole and it is 0.9, and it's the Kerr black hole, the entire range of black hole spin if we study, then these are the range of black hole mass we can find for in terms of accretion rate. So this is the range. If the black hole spin is 0, then for accretion rate less than 2 Eddington rate, so this is the limit for 2 Eddington rate, the possible range of mass is 175 to 1783, that can produce the luminosity and QPO frequency for this IC4 342X1 source. Now, if the black hole spin is extremely rotating, if the black hole is extremely rotating for a very high spin values, and for the same range of accretion rate, the mass of the black hole reduces between 55 to just around 1200 solar mass. Now, what is most intense here, with these findings, we obtained an empirical relation. This is for the first time we could find it out, that the black hole mass can be scaled with accretion rate with this relation for any black hole speed. So this is a very nice relation. So once you have this relation, you don't need to find out all these different all these calculations related to the accretion physics. So if you know what is the accretion rate of this source, and if you know the black hole spin, immediately you can calculate what is the black hole mass. So, and you can see this empirical relation fits very, very well, irrespective to the range of black hole spin, all these dashed line. And finally, we emphasize that this is the range of Eddington rate. Now, if the black hole, which is present in the IC 342X1 source, if it's a stellar mass black hole, then its accretion rate has to be above Eddington rate. So this will be related. This will be for this range if the mass of the black hole is less than 100 solar mass. So this is the final outcome of our result, and I think we are almost out of time. So this is the conclusions. The conclusion is very, very definite. I'm not going into the details at the first 3 points, or maybe the first 4 points. I try to emphasize the final point. What is this? It says that if the ultraluminous X-ray source contains this IC 342X1 source contains an extremely rotating black hole, and if it accretes matter at the super Eddington rate, then its mass has to be less than 100 solar mass. So this is the final outcome of our studies. So with this, I will stop it here. And once again, I thank the organizer to present my recent work. I will be happy to answer any questions related to that. Thank you.
Okay. Thank you, Professor Santaberta Das, for your timely talk, even though it was difficult for 15 minutes talk. So now audience is open for question and answers. So any queries from participants? So please feel free to turn on your microphones and have 2 or 3 quick queries from participants.
Okay, sir.
Put your question in.
Hello.
Yeah.
Okay, sir. Santaberta Das. So I just want to know something about this. From your conclusion of your work, it seems that it can be stellar mass black holes also, or it can be intermediate mass black holes, right?
Yes, sure.
So the situation is depending upon what kind of accretion it's going on. So
yeah, please, complete your question.
So of these two, which model you prefer? I mean, which model you think it would better fit this particular IC 342X1?
Well, the entire catch here, you see, we left all the possibilities here. The reason is we do not know what is the spin of the black hole, which is sitting inside the IC 342X1 source. So this is one limitation. Another limitation is we do not know its mass. So if we definitely know one of these properties, at least spin or black hole mass, then we can constrain its accretion rate more accurately. Okay. What is more emphasizing here?
Either of these can happen.
Yeah, I mean, let me allow another 30 seconds to explain your question. So another catch is why we emphasize our model is really a effective model, because we try to explain both timing and spectral properties together. And since the accretion physics are responsible for explaining both timing and spectral properties, both, So, and what we have tried. So once you fix the black hole spin, then your job is very simple. Okay, so you cannot have all parameters free, then it's difficult. That's why we have given the ranges. So for example, you see in the future endeavor, if someone's identified or some work identified its spin, definitely you can use this range of mass and accretion. But at this
Uh,
moment, we are tied up. We cannot say anything, which is better, which is not, because these are all possibilities.
Yes, actually, these sources, since they are most of the sources, they are very much far away from us. So, is there
Yes.
any possibility, yeah, for this black hole spin to be estimated somehow?
Yes, I cannot rule it out the possibilities. Obviously, it is possible, but the major difficulties is the lack of observations.
Yes, I do. Yes. Thank you,
May I
sir.
know with whom I spoke? I mean, maybe in future, even
Yeah,
it
I
will
am
be.
actually, sir, I am Senorita Devi. In the last session, last talk of today's morning session, I also have a talk on this
Okay, no, no,
ultraluminous
no,
X-ray
very good, very
sources
good.
overview.
Actually,
This is the
I'm
basic
extremely
overview.
I'm
Yes, sir.
extremely sorry that the last two editions are happening online, and it's really creating a lot of trouble. I mean, I
No, sir, it's
personally
okay.
wanted to visit Arunachal. I never been there, although I am here in Guwahati about more than 12 years or so. But I was very happy
Okay,
that
I
I
am
will
from
go there.
Manipur University,
Oh, you are
and
from
I have
Manipur.
also, yeah, yes, I have also been working in these ultraluminous X-ray sources.
Okay,
But
it will be
yeah, yeah.
great that
So I'll
I'll
be
listen your
presenting my
talk.
talk.
Okay,
Okay,
sure,
sir.
sure.
Thank you very
Okay.
much. Mhm.
And please don't call me sir. I mean, I don't really like it. No.
Okay.
Any other questions, I would be happy to answer.
Thank you, Professor. So we also miss here in Arunachal Pradesh, sir. So any other queries from participants? Okay, sir. I have one query, sir.
Sure.
Yeah, for our knowledge and understanding, sir. Please elaborate on how you consider your effective potential, theoretically and observationally. Describe your accretion flow model. And why is your model, you think, fit to ULX source like IC342X1, sir?
Well, actually, so this is the potential. Okay, so this potential is basically calculated from the general relativistic framework, and practically it is not really. Let me see if I have any slide for that or not. But in any case, I mean, don't go into that technical details. What I'm trying to say is, if you deal with the uh, energy momentum tension and study the fluid dynamical properties considering these, then you can write down the momentum equations in the form of derivatives. And one of the derivatives, you can identify something like this term, not exactly this term. So once you compare these terms with the Newtonian approach, then you can say that they are mimicking. Okay, and also we tried our potentials with the general relativistic calculations, and we compared it, and we found a very good comparison. I mean, possibly the best comparison ever exists in the literature so far. So this is the way we can confirm that this potential is really doing great job for studying accretion physics with them. And secondly, why I feel that our model can be useful to study the ultraluminous X-ray sources. So if you notice this point, that the way we started, that if the ultraluminous sources are really accreting black holes, okay, we are not really sure whether it is the case, but if it is the case, then definitely our model is suitable to explain it, because the entire model is developed based on the first principles, the governing equations, conserved equations, and it is valid for black holes of any mass. So this is the way we can say that our model can be used to to study the ULX sources, provided these ULX sources contains a black hole at that center.
Okay. Okay. One more. In your Bernoulli equation of, I'm sorry, there is some background noise. In your
Hello,
Bernoulli
sir.
equation of,
Biplab here.
Yes, Biplab, please tell me.
okay, yes. Yes, yes,
Yeah.
please carry on.
I hope I'm audible, sir.
Yes, Biplab, tell me.
Yes, sir. Yes.
Yeah. So, sir, since you have considered all the cooling mechanisms, as you mentioned, Bremsstrahlung, synchrotron, and Comptonization, could you please elaborate on what is the magnetic field configuration in your model?
This model we use the stochastic magnetic field. Structured magnetic field we didn't use yet.
Okay, sir. I see. Yeah, that was
Okay.
my
What about the? Yeah. So what about current, that is spin parameters in your accretion solutions? It seems to imply not only the so eating just accretion rate. So for our understanding, please explain why it seems to play no role for spill parameter in the accretion rate, sir. In independent accretion rate, I mean there.
I didn't understand your questions. So can you repeat once again?
Yeah. So in the that is the accretion rate in the plot in the plot. So
Okay.
it seems to that spill parameter seems to imply no round in that accretion rate.
Are you saying this plot?
Yeah. I cannot see from. I'm sorry. Yes. Yes, sir. Yes, sir.
Okay. So in this plot, we use the black hole spin fixed as 0.99.
Okay, it's here. Yeah. Also, what about the Eddington accretion rate? At the Eddington accretion rate.
In the x-axis?
Eddington accretion rate, sir.
I'm sorry. I actually I'm not really sure what you are asking. Eddington accretion rate is defined by considering the fact that if there is a spherically symmetric object which is gravitationally pulled and at the same time radiation pressure is also supported. So once these two things are balanced, and from there you can calculate the Eddington rate. So black hole spin does not have any role there.
Yes. My question is
still,
that
I'm not sure what you are asking. I mean, if you don't mind, can you please ask once again?
Okay. So my another question, yes. So measure round of that spin parameters in your accretion solution, sir. Measure rounds of your accretion. Yes.
Okay. So are you asking how the accretion parameter affects our accretion solution? Sorry, spin parameter affects our accretion solution?
Yes, sir.
Okay. So actually, in all the plots, most of the plots, we did not change the spin of the black hole. The reason is we didn't include many possibilities. But here you can see that in the last plot, you can see that we have done the calculations both Schwarzschild black holes and K black hole. So in principle, all the plots that I showed, it is possible to reproduce for black hole spin of any value.
Okay. Yeah. Thank you. So any other questions from the audience, please? Okay, so okay, there is no question in the chat box as well. So no questions. So let us thank Professor Santabarta Das for his nice talk once again. Thank you, sir.
Okay, thank you. Please don't call me sir.
Okay, thank you.
Okay, thank you.
So So our next speaker is Professor Deva Prasad Maiti. So he will be talking on the topic dynamics of reheatings and its observable effects. So may I call upon the Professor Deva Prasad to share his talk, please, sir?
Can you hear me?
Yes, yes.
Okay, okay. So let me share my slide. Okay, I hope you can see my screen.
Yes, yes, yes. It's coming out. Yes, it's visible now. So can you make it a full screen?
Yes, I mean, is it now visible?
Yeah. Yes, it's visible. Yes, yes, it's visible. You please start.
Okay, thank you very much for inviting me specifically, and I also apologize for not seeing the mail on time because of this spam folder of this Google. So all this NEMA mail somehow is entering in my spam mail. So I couldn't find any mail in the general inbox. So anyway, so that is the technical one. So today, I think before I start, let me thank the organizer for this beautiful conference, online conference. Anyway, I would love to be there at Arunachal Pradesh, but now because of this pandemic, we could not. So hopefully next time, if possibilities come, then we can meet together. So in this talk, what I'll be talking about is a very early phase of the universe, and try to understand that early phase through the present observables, or in the sense that because we are living at present, so that means everything that we want to understand in the early universe has to be whatever we see today. So basically what our goal in order to understand any cosmological phenomena in the early universe is to propose some nice observable at the present universe, such that we can connect the present observable with the early universe, whatever has happened in the early universe. So this is one of the attempts that we have been working on. And we have taken a specific phase of the early universe, which is called reheating. And in today's talk, what I'll be basically mentioning is that the specific observable that I'll be mentioning is the gravitational wave, which has recently gained widespread interest due to large number of experimental proposals for detecting this gravitational. Okay, so you all know that with the current understanding of the cosmological universe, if you go backward in time from the current cosmological constant dominated universe to very early universe, then we will start to see first the cosmological constant, which is present, and then you will have matter dominated. Can you see my the pointer?
Yes, we can see.
Okay. So if you go backward in time, what you observe is that if matter dominated phase, then radiation dominated phase, and then if you believe in inflation, then there will be an inflationary phase. So what my interest is the intermediate between the inflation and radiation, and that is the reheating. Okay, so this is the particular phase that I'm interested in, and I'll be talking about why I'm interested in the next slide. Okay, so what is reheating phase? In order to understand the reheating phase, first thing that we have to understand what is inflation. And we all know inflation is essentially the meaning of the inflation in the context of early universe cosmology is same as the meaning that you all know in the context of inflation of like present inflation of food price and all that. So basically, it is exponential raise of exponential expansion of the universe. And moment you assume that there is an exponential expansion of the universe, then you immediately realize that that there will be nothing. So everything will die. Okay, so that means you will land up with a space which has nothing. So if we assume this cartoon diagram, and this the left side of this cartoon diagram is the inflationary phase, and this can be nicely modeled by a simple scalar field. I'll come to this at some point. I will mention that. So this part is the inflation, and what happened during this inflation is exponential expansion. And moment you have this exponential expansion, nothing will exist. So finally we land up with a space which has nothing. It's just empty, except of course the energy that is there, because who is causing this inflation. That is called inflaton energy. Okay. So that means now I have this empty universe which is created by the inflation, but you need to produce everything what you see today, because that is what is there already that we see today. All the matter fields, say radiation, dark matter, cosmological constant, whatever you see, gravitational, has to be produced at some point after the end of inflation. Okay, and that precise phase is called reheating phase. So you have to end at some point, because you cannot eternally do this inflation happen because then you will land up getting nothing. So you have to have this a phase, intermediate phase, which is reheating, during which all the particles that you see around, or that you see today, all the matters that you see today, cosmological constant, everything that you see today has to be produced during this phase. And you can see there is I will repeatedly use this cartoon diagram of this waterfalls, and they are pretty much the same. So you can clearly see here, when water falls down on the ground, then you will end up getting the very complicated process of forming steam, bubbles and all that. And exactly the same thing happens during the reheating. So it's extremely complicated process, non-perturbative process, non-equilibrium process. So, but it happens at very early universe. So naturally you would expect that it is extremely difficult to observe in the present universe, because it happens very early universe, and since it's a non-equilibrium and highly complicated non-perturbative process, we all know that at some point our universe has to be thermalized, because otherwise you cannot explain whatever you observed in terms of CMB and all that. So that's why everything has to be thermalized after all this complicated production. So moment something is thermalized, you all know that thermalization, after thermalization, all the information about what happened before is washed out, typical. That is what we expect. If you have a gas or box started with a very specific initial configuration, then you will let it release, then finally it will thermalize. But then once you have a thermalize, it's very difficult to say from which state the thermalization comes. Okay, so that is why typically this reheating phase is extremely difficult to observe. But we need to observe, because this is a process. This is the phase where all this process happens, and you would expect there are various new physics should appear, because inflaton is anyway part of the new physics that we know of in the context of standard model that we currently know. So that means the new physics that you expect, if you think of any new physics, there is obvious new physics that will happen during this phase. Okay, so that means it is extremely important to understand this phase, and extremely important to theoretically understand this phase, and also observational to understand this phase. Okay, so what do we expect? What are the things that we should expect once this thing happens? Because naturally we expect cosmic microwave background, we expect dark matter abundance, and we expect primordial gravity. Those, because all these are essentially the components. CMB contains photon, dark matter contains any kind of fermion or scalar. PGW, which is primordial gravitation. I'll mention this because this is the topic that I'll be talking about. So this is the and various other the visible matters that we see around. These are the observable quantity that we know. So what my goal would be to look at this particular phase through a specific observable called primordial gravity. Now you see how that particular phase is getting imprinted into a particular observable called primordial gravitational wave. Meaning, when I'm saying observable, it means some quantity which essentially measuring the energy density of the primordial gravitational wave. Okay, so this is the plan. So I have already motivated you that what I'm going to do and why I'm going to do. And then I will give you simple model of reheating, which is not very important for me, because as long as you know what if there exists a reheating phase, then what would be the imprints of that reheating phase on the gravitational wave? That is what I'm going to talk. Okay, so this is the. Let's not worry about all this complicated equation right now. As long as you understand the basic part. What is this basic part? Basic part is inflation happens and then ends, and then after the end of inflation, you have all sorts of production. What are the production? During this reheating, you will definitely have inflaton energy density. You will definitely have radiation which will be produced from the inflaton. You will definitely have dark matter. You will definitely have gravitation. So all these things will be there during this reheating, or also before the reheating. So, but before the reheating, you would expect naturally the radiation dark matter will be very less, because everything will be diluted. But we'll talk about gravitational wave specifically that is produced before the reheating. Anyway, so the energy density of the gravitational wave anyway is expected to be very small. So that is why we can simply model this reheating by just inflaton energy density and then radiation production and dark matter production. So this is a complicated equation. Let's not worry about that. As long as we understand that there exists a phase, that is enough. So now we will solve this. So we model this reheating by this complicated Boltzmann equation. Then now what we'll do, we solve it and then get the background. Okay. Okay. So in order to solve it and create the present universe, we have to start from the inflation, because as I told you, we have inflation and then reheating, and then subsequently all the standard phases that you already know from the experiments. Okay, so that means the model of inflation, I take a specific model of inflation which is guided by this potential. Okay, and this is called alpha attractor potential. So name is not important here. So this is, if we draw this potential, I have different, depending on various parameters, will look like this. You can clearly see the potential looks like exactly the waterfall diagram. So you have inflationary part, which is flat part, and then at some point this will fall, and then there will be a complicated reheating phase will happen. Okay, and if you look at this, that depending on the various parameter, I have drawn this potential, but as you go far away from this minimum of the potential, all the potential will boil down to almost the same form. That means inflation is already constrained by a specific observation, which is by Planck. Okay, so Planck observation will essentially give you how inflation has happened, how inflation has started. Okay, so that will give you a constraint. So that means I cannot arbitrarily roll down this water towards the ground. I have to have a very specific initial condition, and that initial condition is guided by whatever you observe today in CMB. Okay, and this is the plot, which is Planck CMB, famous plot that many of you may have seen. So this once this initial condition is set by set means I want to produce whatever CMB have observed, then accordingly I set my initial condition, then inflation happen. Inflation start to happen, the initial condition, and then it will roll down, inflation happens, and that sub point inflation ends, and then you solve this whole thing starting from the beginning to the present state. And this is the cartoon diagram on the right, where the left black line, which is essentially telling you that how inflation happens, and then this almost horizontal line, this blue, various blues and these reds, they are essentially telling you how reheating happens during this phase. And then the rest of the parallel three lines, so it is red line and then this one, these are telling you standard Big Bang, which is essentially radiation matter and all that. So this is this cartoon diagram essentially captures the full dynamic starting from the inflation to the present universe. Okay, so now that we have this background in between, background with a specific phase called reheating. Now what I'll do, I want to see what kind of observable can encode the information about this dynamics, such that if I look at that observable and then analyze that observable, then whether from that analysis we can actually talk about that whether this reheating happened or what are the properties that I can extract from the observable. So what I'll specifically talk about is essentially, and I should mention that because if you look at the minima of the potential, different parameter will give you different shape of the minima, and different shape of the minima of the potential will give you different kind of character, and that is parameterized by something called equation of state. So that means if you take different potential or different form of the minima, you will have different evolution, like here dotted blue and solid blue and the solid red during the reheating phase. So that is precisely so different potential will give you different inflation background dynamics, and then if you try to look at how the present observable and how those different character will be encoded in that present. That is what I'm going to do, and I'm going to talk about how inflation, how gravitational wave is getting imprinted into gravitational wave will look at this whole background dynamics. That is what I'm going to tell. Okay, so what is gravitational wave? This is essentially ripples in the space-time. Okay, it means it essentially telling you, if you think your space-time as a kind of fluid, but it's extremely rigid fluid, and then you have a very high energy process happens at some point in the space-time, then according to Einstein, you start to get a ripple. Okay, and that ripple is essentially the gravitational wave. This is a diagram that you have already seen in your previous lecture, in the studies lecture. So this is because it's a ripple on the space time. It is same as like electromagnetic. We can all sorts of frequency range. Okay, and depending on what kind of processes happen, you will get various ranges of frequency produced from this process. Like if you look at this, you have various like ground-based detector, space-based detector. And this pulsar array that I studied, there was a talk on this. So various sources of gravitational wave will give you a specific range of frequencies, and then you build up a detector, and then you observe this. And today, what I'll be talking about very extremely high energy source, and that is called this inflation. Inflation plays a very beautiful mechanism of producing gravitational wave as well. And what is interesting about this inflationary gravitational wave is that it actually produces, if you look at this picture, it actually produces all sorts of frequency. It is not that it produces only a very specific range of frequency, but it produces all sorts of frequency to equal importance. So that is very important. So that is why it gives us a very interesting possibilities, that because we have large number of detectors now in space and ground, they are proposed and they are already been detected. People are observing, so they might see this. If all this experimental sensitivity is very large, they might see this gravitational wave that is produced from the very early universe during the inflation. So that is what I'm going to show and see how that gravitational wave actually imprints the phase of reheating. Okay, what is inflation? That I already told you that this is essentially a ripple in the space-time. So if you think, this is the ripple, this part is the fluctuations on the space-time. If you put that to be 0, that is the standard cosmological universe. Now this h mu is the ripple on that space-time. Okay, and this h is essentially the gravitational wave, and you all know that this gravitational wave has two mode polarization. These are the various polarization that you can calculate by simply calculating this equation. So what I'm going to do now, so inflation is a beautiful mechanism which essentially plays like an amplifier, and because you all know from the quantum mechanics that any fields that you consider, you always have quantum noise. Okay, so you always have quantum fluctuations. So what inflation does is essentially it enhances that quantum fluctuations and produce a classical gravitational wave, and that is what we see today. So this is a very interesting mechanism. It is like giving like a quantum. It is like amplifier circuit where your input is a quantum noise, and the inflation essentially amplifies that quantum noise to a large extent. And then that is what we see today. And because it's a quantum noise, it essentially have all possible frequencies, because quantum noise contains every frequencies. So that is what is happening, and this is what our result is. One of the results that I just wanted to tell you. So if you look at this figure, this is the figure that is the main point. So where I have plotted various experimental sensitivity curves. As I told you already, because inflation can produce all sort of frequencies starting from 10 to the power minus 11 to 10 to the power 9. So, and you can see here that depending on various phases of the I think I should tell you, because this various inflationary reheating phase means you take various dotted blue line, solid blue line, and all this red line. So based on that, you see here that gravitational wave spectrum will follow accordingly different, will imprint that information. So this part of the frequency range is the frequency range which is very large wavelength region and which typically does not see the reheating, but these are the part where you can see clearly different spectrum, and this different spectrum corresponds to different dynamics during the reheating phase. Okay, so if you take this red line, let's say, then that you will get this pink, or this pink and blue, this green curve is corresponding to this red line. So that means what you can see here, as gravitational wave, this quantum noise is enhanced by the inflation, and then that gravitational wave will pass through the whole ray throughout the background. Okay, it will see the radiation, it will see everything, and as it goes along, its amplitude will be disturbed, amplitude will be evolved accordingly, and this is what precisely encoded here. So these various lines, pink, blue, and these lines are essentially telling you what is the equation of state during the reheating. So this phase is particularly the reheating phase, which is encoded into the gravitational wave. So that means so this is the observable that we see today. So that means today, looking at the power spectrum, the spectrum of the gravitational wave, we can actually see how how this reheating happens. Okay, so this is what is the main conclusion of my discussion. I can go into various details, but let's not talk about those details. But what is the basic message that I'm going to tell you is that if there is a gravitational wave, if it passes through various phases of the universe, it can clearly imprint various phases of the universe, and that's how we can get very important information about what happened actually in the early universe through this gravitational wave. So okay, that is the main conclusion, that is the main point that I wanted to tell you. And if you want more detail about this and various information, then you can go through our paper that you have recently put up. Okay, so let me conclude. I think I don't know how much time I have, but anyway, so reheating is a very important phase of the early universe. We all know the standard Big Bang phases by various observations, but reheating is the phase which is typically has not been observed directly, or in the sense that it is extremely difficult to observe because of the thing that I have already explained before. So it is important to observe this phase because it contains various new physics which we need to know in order to understand in order to fully understand the present the physics of the universe. If you want to fully understand, we need to understand the reheating phase. And as I told you already, I emphasized you, gravitational wave plays very important role in order to see that particular phase. Okay, I think I should stop here. And if there are questions, then I'll be happy to answer. Thank you.
Yeah, thank you, professors. Thank you. So any questions on the talk from participants? So any queries?
Hi, I have a query.
Yes.
Hello?
Yes. Yes.
I'm Indu. So, no, I would like to ask about the James Webb telescopes. What kind of information that may give about this period of this era? Can you?
Which telescope? Any
Now,
telescope?
the recently launched James Webb telescopes.
No, James Webb telescope. I mean, those are the optical telescope. No, it's not a gravitational wave detector.
Yeah, right. No, from that era, if we want to see that era from the James Webb telescope, then what kind of information we may get?
Look, that is what I tried to mention. I've not talked about this in detail because by using I would say by using electromagnetic wave, it is extremely difficult to see that particular phase because you see electromagnetic wave is highly interacting
Right.
with the particles. The moment it produces any during this phase, radiation will be produced, but that radiation will be highly interacting in subsequent phase. So naturally, what will happen? All the information about this phase will be erased because of that interaction, because it's strongly interacting with the charged particle.
Okay, that means no, because what they claim is that they want to see this this particular era using the James Webb telescope, right? So
No, they want to see which particular era.
no, this after the Big Bang and this heating and this phase when
Yes. So they are not talking about reheating phase anyway. So they are talking about after the Big Bang. After the Big Bang means your thermal, this reheating has already happened. Then you are deep into the radiation phase, and then if you talk about you can talk about very high energy photon from that radiation. So they don't talk about reheating phase anyway.
no, I don't know the details, but what they say after the Big Bang they want to see. That's why I thought.
Yes, after the Big Bang means typically when generically after the Big Bang means they start with the radiation phase. They don't talk about reheating.
Oh, okay.
That is the generic way of saying after the Big Bang.
Okay.
Yes.
That means okay. For this, you are suggesting gravitational wave would be better.
Gravitational wave plays very important role. Yes. And there are other observable that we are currently looking at. Of course, if you look at very small scale structures, that may encode, but that is extremely difficult because at the small scale we know that gravitational instability again will essentially erases those small scale structures. So that is why gravitational wave actually give you very clean signal about this phase.
Okay, I have one question, professors.
Yes.
Please enlighten us that for that important major role played by that heating to cause the phase scenes from the inflection to radiation in the
Yes.
evolutionary phase of the universe. Please,
Yes.
sir.
Yes. Hello.
Yeah, you hear me, sir?
Yeah. So I'm what is your question? So inflaton
my question is that the important roles played by the mechanism of heating, so to cause the phase scenes in earlier times from inflection to radiation in the evolutionary phase of the universe. I mean,
Yes. So what happens is that so you start with inflation, okay, and then this phase. This phase is not an instantaneous phase, okay. So this decay process that is happening because you have to get your present state of the universe, and if you want to get the present state of universe, this inflation has to decay completely, and this is not an instantaneous process. So what will happen? This process of transferring energy from inflaton to various other particles will take some time, and that will give you an extra phase, additional phase in the early universe before reheating, before the radiation that we standard Big Bang know. When you say standard Big Bang, we start with radiation, then matter, and then present cosmological constant. But what we are suggesting, what we are saying is that before this radiation and after the inflation, there is a prolonged phase, which is this reheating phase. And that has to happen, and it is not instantaneous. So that is why I'm saying that if you want to really see this phase, gravitational wave plays very important role. So it is an additional phase compared to, I mean, it is an additional phase apart from inflation and also radiation. Is that answered your question?
Yes, sir. Okay, sir. So any others questions from participants?
Hello.
Yes.
Sir, I mean, this particular graph of this potential versus this phi. So if we see the evolution, we can see that after this cooling happens, it went to a stable equilibrium kind of state, right? I mean, where the ball is dropping.
Yes. So if you look at this right to the waterfall figure, so
Yes.
what will happen? All this complicated process happen that after some time everything will cool down and then you get water again. Exactly.
So this particular point is a stable equilibrium point, but there you are saying that reheating happens. So again, the graph starts to evolve in upper side.
Which graph?
I mean, this potential.
No.
graph that you have
Okay.
drawn.
So this is just a cartoon diagram. I think I should talk like this one. Okay. So you can have different type of potential, but it has to have like bounded from below. Okay. And then what will happen that this ball will roll down, and then what will happen? It will start to oscillate, right? And then moment it oscillates, because it's a quantum fields, so it will start to produce, it will start to transfer its energy from inflaton to other fields. And then gradually what will happen that this oscillation will damp down gradually, and then it will become settle at this point. And then that means by that time all your inflaton energy is getting converted into. So what will happen? This potential will no longer be there anymore, because the potential energy will getting converted into the kinetic energy or to the other particles, not the inflaton particle. So that is why this potential will vanish. So scalar field will at some point vanish. Nothing. Scalar field will not be there anymore.
So this oscillation happening in this stable equilibrium region is actually generating this kind of gravitational wave that you are seeing. That wave is coming from this oscillation itself, right?
No. Here I'm not talking about this production of. So basically, you are right. That's an interesting question. So the production of gravitational wave during the process is extremely low, actually.
Okay.
So you will see that actually production channel, if you so basically inflaton will couple with all the other matter fields, let's say electron and then photon and then graviton. Now what will happen is that production of gravitational wave, if you look at the probability of cross section, we will find that production cross section is extremely low for graviton, but production cross section is extremely high for radiation and photon. That's why most of the production will be happening towards the radiation, fermion and photon. So gravitational production will be extremely small. But here, what I'm saying, there is another production during inflation, which is there is a quantum noise, and inflation plays like an amplifier. So what will happen? This quantum noise, all the modes of this quantum noise of the gravitational will get amplified because of this this inflation, and that is what I'm trying to see. And then it will evolve throughout the whole space-time, and how it is encoding various phases of the universe. That is what I'm trying to see.
Okay. Thank you.
Okay, Professor, I think we have one more questions in the chat box.
Okay.
It's a question questions are from Pastor Norbert Kirmi. So his question is there any possibility that the gravitational wave will be able to give us any information before the Big Bangs?
No, that is my point. I think somebody Indu was asking these questions related to Big Bang. It typically is a loose word. I mean, what is the starting point of the Big Bang is not very precisely mentioned in this statement when you say Big Bang. So basically, it is better not to use this word Big Bang. It is better to say our universe has evolved through various phases. If I assume that my first phase in inflation, then reheating has to happen. So inflation, reheating, and then radiation, matter, and present state of the universe. Okay. So now you have to ask before which phase. In this question, the question that I was saying, before which phase he is talking about or he is talking about. So when you say before Big Bang, if it is before radiation, then of course I have talked about this. Before radiation, this radiation reheating phase is there. And if you say before reheating, there is an inflation phase. I have talked about the inflation. But if you say what happened before inflation, that I don't know. In fact, it is not known in some sense, and it is not interesting at this moment, this question actually. Of course, I think there are people have talked about pre-inflationary universe, but I think that is right now it is not that important in the sense that those are not observable in some sense.
Okay, Prabhu.
Okay, first of all, I think I should say there is this professor. I'm not professor anyway, so you can remove this professor designation from me. I'm not professor yet. Yeah. So I'm just same as you, colleague. So,
Okay.
yeah.
Oh, yes. Thank you very much. So there is no other questions from the participants. So let us thank Dibu for his nice talk. Thank you, Dibu.
Okay.
Thank you. So we have as speakers, so Dr. Ablu Maitai. So he will be giving his talk on the topic quantum gravity effect on the Hawking radiation for some black holes. So I request Dr. Ablu to share and start your presentation, please. So you are given to 15 minutes. 10 or 12 minutes for your presentations and 2 or 3 minutes for the question and answers. Please. So, Dr. Ablu, are you over there?
Yes. Okay, I'm.
So please, kindly see your presentations.
Yeah, I'm sharing the. Okay, can you?
Yeah, it's coming out.
Okay.
Yes, it's coming out. Yes, we can see now. So please make it full screen. Your presentation, if possible. So it seems to be.
It's coming.
Yeah, it seems to be small. So please start from the beginning, if possible.
Okay, can you see the slide?
Yes, we can see clearly.
Okay, thank you, Sanjit.
Yes,
okay, actually, I also wanted to visit Arunachal Pradesh because I have never been there, even though I stay in Imphal. So it's very unfortunate. So at some point of time, we'll surely visit this Arunachal Pradesh.
Sure.
And today, the title of my presentation is the quantum gravity effects on Hawking radiations of some black holes. I'll discuss the quantum gravity effects in the framework of the generalized uncertainty principle to study the changes in the Hawking temperature of the three types of black holes, and the short-cell de Sitter black hole.
Excuse me, Dr. Ablu. Excuse me. Kindly start from the beginning. So your slide is in the discussion slide.
Yeah, I'm starting. Huh? It is
yes,
discussion.
And then the slide is not moving.
Okay. Let me then start from the beginning. Okay.
So kindly share your presentation from the beginning.
Here it's coming in the beginning. Okay. Okay. So I'm just correcting it.
So, Dr. Ablo, your voice is not audible.
Okay, okay. I'll just. Okay, so can you see the slide? The beginning of the slide.
Uh, no,
It's
no. You
from
please share.
huh?
We can see.
You can see.
Yes, sir.
Is the
No,
beginning of the
no,
slide? No.
no, no. We can see your slide.
Okay. Is it is the title slide?
No, no. What I'm saying is, I can see here in my laptop your slide.
Okay. I'm asking, is it the title slide or is it the is it some
No,
other?
no. You please share your presentation. Yeah, it's coming out now.
Okay.
Yes, yes. We can see now. You please start.
Okay. Okay. So I'll be discussing the three classes of black holes: the short scale de Sitter black hole, rotating BTZ black hole, uh, and the Kerr-Newman black hole. So classically, the black holes do not radiate. Okay. The gravitational force of a black hole is so strong that even the light cannot escape from the black hole. However, in the early 1970s, using the ideas of the quantum field theory in curved space-time, Stephen Hawking showed that these black holes emit the particles, and the energy spectrum of these particles was found to be the thermal, and which implies that the black holes must be in some thermal equilibrium uh, at some finite non-zero temperature. And this temperature is known as the Hawking temperature of the black hole. And the Hawking radiation consists of all sorts of particles emitted by the black hole. This is the fermions or bosons, etc. Uh,
So,
is,
excuse me, Dr. Ablo. Please
is the
change
slide,
your slide, and then they
is,
click at the slide that you are showing.
okay. Okay, then.
Please click on the slide numbers on which you are talking.
Okay.
Click on the slide.
Okay, I'm just escaping. Okay. Okay, so
Oh, yes, yes. You please. Yes, yes. You do that.
from here it will better, I think.
So you please start. Kindly start from
Uh,
where you have stopped. Yes.
can you see the slide? Is
Yes,
it
yes,
there?
yes. You please carry
Okay,
on.
so in the uh, in the atomic and sorry for the technical glitch because here the slides are changing, but I don't know, the slides are not changing here. So sorry for the glitch. So in the atomic and subatomic scale, the Heisenberg's uncertainty principle provides us the basic limitation on measuring the positions and the momenta of particles. And however, there is no absolute minimum uncertainty in the position or minimum or momentum. And however, if one of them is fixed and there is a conditional minimum on the other quantity of it. So, however, when we include the gravity to the quantum theory, okay, and some changes takes place, and the various theories of the quantum gravity, like the string theory, the loop quantum gravity, and the W special theory of relativity, predicted the existence of a minimal observable length. So when the quantum fluctuations of the gravitational fields are taken into account, a minimal length of the order of the Planck length is observed. It results, okay? It's not observed, it results, and the minimal length may be regarded as the minimum position uncertainty. And so, accordingly, we have to modify the uncertainty principle, and in the presence of the gravity, the Steiner-Heisenberg's uncertainty principle results to the generalized uncertainty principle, and the simplest form of the generalized uncertainty principle is given in equation number 1, okay, where the beta is given by beta naught times LP square by h bar square, where LP is the Planck length. And if we remove, in the absence of the second term in the right hand side, we get the usual Heisenberg's uncertainty principle, and and in this generalized uncertainty principle, we cannot decrease this delta x indefinitely, because if we decrease delta x, delta p will increase, and this increase in delta p due to the quadratic term in the right hand side, the right hand side may become greater than the left hand side. So there has to be a minimum in the position a minimum in the position uncertainty, and this absolute minimum in the position uncertainty is of the order of the Planck scale. When we calculate using equation number 1, we find it to be of the order of Planck scale. So that's why we have used this form of the generalized uncertainty principle, and then this generalized uncertainty principle. Using this generalized uncertainty principle, the Klein-Gordon equation is also modified, giving us the generalized Klein-Gordon equation. And then, in order to solve this equation for the particles, okay, for the scalar particles, we use the wave function given by this equation number 3. Okay, here I is the action of the scalar particle, and then we considered Hawking radiation of the Schwarzschild de Sitter black hole in the presence of the quantum gravity effects. And so we by considering this, the line element of this Schwarzschild de Sitter black hole, and we solve the generalized uncertainty principle, and the generalized uncertainty generalized Klein-Gordon equation, okay, in given in the earlier slide, and then we can find the Hamilton-Jacobi equation of the scalar particle given by this equation number 5, and then we use the action of the particle in the form given in equation number 6, where omega is the energy of the emitted scalar particle, and then then we solve and then we solve the Hamilton-Jacobi equation, and giving us equation number 7 and 8. Okay, and this 8 gives us the radial part of the action, and finally we get the two meaningful roots, and the corresponding imaginary part of the action are given by equation number 8 and 9.
So we cannot hear. So there may be some network issue. So Dr. Ablu, so we are not audible to you. Okay, so there may be some network issues. So he has left. Oh, okay, so so we'd like to move on So moving on, we can have next speakers. So Bhaskar Goswami,
Yes, sir, I'm
over there.
present
Yes,
here.
yes, yes. So, okay, so yes, Bhaskar Goswami is giving his talk on the topic investigating the correlation between the polarization maximum and the minimum for the spheroidal particles. So, uh, so I request Bhaskar Goswami to start your presentation, please.
I hope my screen is visible.
Yes, yes, yes. So you have 15 minutes. You please try to complete uh, within 15 minutes. So 10 minutes are for your presentations and the 2 or 3 minutes are for your question and answers on your talk. So
Okay,
please
sure.
start.
Sure. So my talk is on investigating the correlation between polarization maximum and polarization minimum on spheroidal particles. So at first I'll talk about cosmic dust on which I'm working on. Like cosmic dust is an abundance element in the universe. It's found in almost everywhere in the universe. Uh, Depending upon the position, we can uh, name them. Like if it's between interstellar medium, we can call them interstellar dust, and if it's in between circumstellar medium, that's circumstellar dust, like so on. And the range of the dust can be from 1 millimeter to the larger particles also, where we can say meteorites also in we can categorize meteorites in form of dust also. The study of dust can give us various informations like the formation of the solar system and different evolutionary processes that we are going through till now. So the study of dust is very much important for knowing our existence in the universe. So I'm studying the polarization properties, so I won't go on detail about what's polarization. I'll just simply say that polarization is a property applying to the transverse waves that specifies the geometrical orientation of the oscillation. And so, in case of a transverse wave, the direction of the oscillation is perpendicular to the direction of the motion of the wave. And we all know that polarization can be of three types. That the linearity we can have three types of polarization. That's linear polarization, circular polarization, and elliptical polarization. And in case of study of dust uh, or any uh, comet, what we see is the polarization can have a bell-shaped curve where we can find a negative peak as well as a positive peak. So that's negative peak, we call them as polarization minimum, and this positive peak, we call them as polarization maximum. And all the comets and show this kind of peaks actually. If we see here in this image itself, there's uh, plot of polarization curve of gas dust rich comet, where in this other picture we can see a plot for gas rich comets, and both of them show the same bell shaped curves where this polarization minimum as well as polarization maximum peaks are available. So the linear polarization depends on this four parameters actually. That's lambda, the wavelength of the radiation, theta, the scattering angle, the complex refractive index, which can also be termed as the composition of the dust. That's m equal to n plus ik, where n is the real part of the refractive index and k is the imaginary part. And then it also depends on shape as well as the size of the dust particle. And the linear function, linear polarization can be defined as with this equation, PR equal to I perpendicular minus I parallel divided by I perpendicular plus I parallel, where PR, the polarization will be zero when theta is either 0 degree or 180 degree. So my study is actually with spheroidal particles, like where I'm trying to model a investigate that whether the polarization maximum and polarization minimum have some correlation or not. As we can see earlier, that almost all the comets or show these peaks, but nobody has ever tried this, that whether these peaks are somewhere correlated in some manner or not. So we have tried this with spheroidal particles for our study, and we tried to simulate this code with t-matrix code, which is a very efficient code to study spheroidal particles, and it is been designed by Mischenko, who passed away last year, sadly. And this code was already in use by our group from the time to time, and it is a very efficient code actually. And study this by applying this code and changing some parameters, we have actually got some correlation to see that whether we have found some correlation in this, and we have changed different codes, different parameters like the real part of the refractive index, the axial ratio, which actually defines the structure of the particle. Like for axial ratio greater than one, it's actually an oblate spheroid, or as well as the if the axial ratio is less than one, that it will be a prolate spheroid. So in the next slide, I'm talking about the axial ratio itself. So this axial ratio will actually give you the shape of the particle. If we change the shape, how this property will look like for this uh, curve itself, we have taken two wavelengths, that's lambda equal to 50 and lambda equal to 65, 0.65. So for lambda equal to 50, if we are changing the axial ratio from 1.80 to 1.90, that is we are increasing. So f from f for every increase in the uh, uh, axial ratio, we can see that the polarization, when the Pmax is increasing, Pmin also started to increase actually. So we are seeing a correlation here, as well as the same thing we can see for lambda equal to 65. Like the for lambda equal to 0.65, we took the acceleration to be 1.20 to 1 and 1.30, and we can see the same correlation here itself. It's actually increasing from 1.80 to 1.90. When Pmax increase, the Pmean also increase in both the cases. But in case of the real part of the refractive index, when we try to increase the real part from 1.65 to 1.75 for 0.50 as well as 0.65, we can see when the Pmax started to decrease, P mean also started to decrease. That is, we can see here that for n equal to 1.6 and n equal to 1.65, this P mean started to decrease from here to here, as well as for lambda equal to 65, the same thing we are observing here, that with an decrease in Pmax, P mean also started to decrease. The thing is, the same thing we can see here as well. Like for R effective, the effective radius, which is the size distribution of the particle. If we do this for uh, lambda equal to 0.50, and we change the effective radius from 0.140 to 1.150 for lambda equal to 0.50, we can see the same relation. That is, with a decrease of Pmax, P mean also started to decrease. So uh, this same correlation is also seen in this 1.5 for lambda equal to 0.65. For R effective of 1.50 to 1.60, it started to decrease. The thing is, if we consider that all the parameters that is we have changed here, uh, for every particular graph, we have only changed its respective parameters only. That is, for here, only we have only changed E. Here we have only changed N, and here we have only changed the effective radius. But all the other parameters like N and E is constant in here. like here the n is around is 1.80 sorry, e is 1.80, but n is 1.65 in this case. Similarly, if we take this for n, we have changed n only, and from 1.65 to 1.75, but we have kept r effective and e constant. R effective is at 1.65, 0.140 for lambda equal to 45, and for lambda equal to 0.65, R is 1.50 in this case.
Sorry, Bhaskar, your time
So,
is going to be over. Sorry.
okay, sir.
Please make it fast.
Okay. Okay. So here we can say that only for a particular range we are seeing this correlation, which is a very important thing, because we can't just get any for any wavelength or any uh, change of refractive index, we can't get this correlation. So for this, actually we have already like for sorry we have already correlated that we have found this correlation of Pmax and Pmin in experiment also, that is Amsterdam Granada light scattering database. They actually used green clay Martian analog and foresight version redboard P type of dust, where they have they actually did this with lambda equal to 633 nanometer wavelength. After getting those data, if I plot those Pmax and Pmin, I also found this correlation in the same for this four dust. So by this we can say that the Pmax and Pmin are correlated, and we also can see that the Pmax started to decrease with an increase in Pmin for every increase in E, but for N and K, both Pmax and Pmin started to decrease for every increment of N and R effective. So we can say that Pmax and Pmin are correlated, but there is also a thing that they maintain that correlation in every case, and the correlation coefficient is found to be around 0. 0.9, which is a very good fit for our result. And thank you for this. If anyone have anything to ask.
Thank you, Bhaskar. Yes. So now audience open for question and answers. Open for questions from participants. Okay. So there is no other questions. So thank you, Bhaskar Goswami, for your nice presentations. Thank you. So I would like to move to the next speaker. So next speaker is Vicky Prasad. So Vicky Prasad will give talk on the topic polarimetric study of comets. So I request Vicky Prasad to start your talk, please.
Thank you, sir.
So you
I'm
have
sharing
15
my-
minutes.
Okay, sir.
So please try to finish within these two bullet times.
Good morning. I hope you can see my screen.
Yes. Please start.
Good morning. My name is Vicky Prasad, and I recently joined in my PhD course in Assam University under the guidance of Dr. Himadri Sekhar Das sir. And in this talk, I'm going to present a brief discussion about parametric study of comet. So the polarimetry study is a very useful technique to study the nature of cometary dust. And comets are thought to be preserve almost pristine dust particles. Um, almost so studying the properties of cometary dust provide us a valuable information about the early state of the solar nebula. So in this work, we study the polarimetric characteristics of comets. Uh, in our work, we analyze some CCD recorded raw images of comets. The CCD recorded raw images have been processed processed by the standard scientific procedure using image reduction and analysis facility, which is shortly called IRAF. This is a software. In this work, we report some polarimetric results, so preliminary results of some comets. So first of all, we let's talk about comet. The comets are mainly consist of ice, rock, and dust, and gas, etc. The comets move the sun in high elliptical orbits, and they have the wide range of orbital periods, ranging from several years to several million years. The comets have three major parts, which are the nucleus. The nucleus is the central part of the comet, and the second part is called coma, and third is called the tail. In this figure, a comet nucleus is shown. The image is the nucleus of a comet 67P. So each comet has a small frozen part called the nucleus. The nucleus is also termed as dark snowball or ice dart ball, etc. The nucleus is mainly consists of ice, rock, and dust and frozen gases. In this diagram, the comet Halley is shown. If we observe this image, then we can see a cloud of gas or dust around the nucleus. This cloud or atmosphere around the nucleus is termed as coma. When the comets come near to the sun, the dust or due to the solar radiation, the ice on the nucleus changes directly to gas, which makes an atmosphere around the nucleus, which is called coma. The coma may be 10,000 to 100,000 kilometer in diameter. When the comets comes close to the sun, the pressure of solar radiation and high-speed solar particles blow the coma materials away from the sun, which makes a tail-like shape, which is called the tail of the comet. There are two types of tails. The first one is called the gas or plasma and tail, and the second one is called the dust or type 2 tails. So now, observing the scattered solar radiation by the cometary dust, we have some results that the wave scattered light by mainly upon the wavelength of incident solar radiation, scattering angle, and refractive indices of the dust material, and shape and size of the dust particle. And the polarization of light scattered depends neither on distance to the sun or the observer, nor the dust space, so dust density for the optical thin medium. In this slide, we present two observations of two different comets. In the figure 1, the polarizations versus so the polarization values is observed at wavelength 0.48 micrometer for the comet Braidfield by Kikuchi et al. Is shown. And in the figure 2, the polarization values observed at the wavelength 0.365 micron for the comet 1P Halley is shown. So in both in the both figures, we can observe that the scattering, the polarization is negative beyond the scattering angle about 157 degree, and in the two comets shows the similar properties. In this figure, polarization versus phase angle plot for two comets, Botany and Jaeger, in different depths are shown. Like the previous plot, we also observe the similar characteristics. Here, we report parametric observations of comet C2 2016 Penster. This is the image is taken by the Samparnan telescope Nainital on 22nd December 2017. The observations were carried out by H.S. Das, B.J. Medhi, T.K. Dhar, and V.J. Chakrabarty. The CCD recorded image data have been processed by the standard scientific procedure using the image reduction and analysis facility, IRAF. And these are some relations linear polarization and quiescence angle of the polarization spectra. We can use these equations and to calculate the linear polarizations from the data obtained from the IR software, and from this data we plot a plot polarizations versus distance from the photocenter of the comet C 2016 Penster. We found the
To say, Vicky, so your time is going to over. You please keep in mind.
Okay, sir. We found the average aperture polarizations for the comma is estimated as minus 0.03, and 0.4% is the error. So using the polarimetry study, we can model the dust particles of the comets. So we in the dust aggregate models, we use some simulations by using T-matrix software to study the nature aggregates. Several investigators built aggregates using the ballistic aggregation procedure. The aggregates have been built using some simulations random hitting and striking the particles together. If the procedure permits a single particle to join a cluster of particles, then the aggregation is called ballistic particle cluster aggregates, or BPCA. If the procedures allows the cluster of particles to stick together, then the aggregates is called ballistic cluster aggregates, or BCCA. And also there are two types of ballistic aggregates, which is ballistic agglomeration of with one migration, BAM1, and the second is called BAM2. These are the references, and thank you.
Okay. Okay, thank you, Vicky. So, do we have some queries from audience? Okay, so there is no questions from the participants. So let us thank Vicky for his nice presentations. Even though he has recently started his work on this area, so you have presented very nicely.
Thank you, sir.
Vicky.
Thank you, sir.
Okay, so moving on, we have a next speaker. So we are a little bit lagging behind our times. So let us try to finish within our stipulated times. So Rajat Chopra.
Yes, sir. Yes, sir. Yes, sir.
So yes, you please. So you'll be giving your talk on the topic about photometrics investigation of dark globules, extinctions, and the distance. You please start.
Yes, sir.
Yeah, it's visible.
Yes, yes,
Please.
yes, 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 sir. Sir, is it visible, sir?
Yes, yes, yes. You carry
Uh,
on, please.
Respected Chairperson, I am Rajashri Pal, PhD scholar of the Assam University Silchar, and also the Associate Professor of Department of Physics, Karimganj College. I am doing my research work under the guidance of the Associate Professor of Assam University Department of Physics, Dr. Himadri Shekhar Das, and my topic is photometric investigation of some dark globules extinction and distance. Before going to discuss about the topic, I'm just highlighting the what are the abstract of this. The determination of distance and of small dark globules is different because its compact size and opaqueness. In analyte photometric technique, we have estimated the extension and distance of a star using the 2-micron all-sky survey, that is 2 mass catalog. However, this technique could not estimate the distance of a star accurately. Hence, using Gaia data, this is the most recently and sophisticated data. The distance of the faint stars in the vicinity of the molecular cloud is obtained, will be used to estimate the extension of the stars. Here in this work, we have reported the distance estimation of the some dark globules by using the NRI technique. Now, what is the introduction? And the studies of the physical properties of the dark clouds of black globules are important for understanding the formation and evolutions of the stars. Photometry and polarimetry are very important tool to study the various characteristics properties of the stars forming the clouds. The photometric measurement of distances to the interstellar cloud plays a significant role to obtain the luminosities of the protostars embedded in the clouds, as well the sizes, masses, and densities of the cloud. Here, in this work, the distance and extensions of small dark globules L1642, that is lines 1642, this is basically a very small cloud I have considered, and this cloud is considered uh, from the data of some of the research papers, and using this, I have to use in this data the technique of NRI, that is the NRI technique we will use in this globe. This is basically what is dark cloud. Actually, dark cloud or debris nebulae is a type of interstellar cloud, particularly the molecular clouds, that is so dense that it obscures the visibility of wavelengths of light from objects behind it, such as background stars and emission or reflection nebulae. Actually, isolated small dark nebulae are basically called as the dark globules. Now, what is molecular cloud? This is the Barnard 6-8 cloud. Molecular clouds are considered as the ideal region for star formation mechanism to occur exclusively inside our galaxy. Molecular clouds in different galaxies are mainly composed of the different gaseous materials in the interstellar medium. And these clouds are cold and dense region of the interstellar medium that is approximately contains 90% of the hydrogen and 10% of the helium and many other molecules. Molecular clouds are considered as the ideal region for the star formation mechanism to occur exclusively inside our galaxy. There are the different types of molecular clouds. Number one is giant molecular cloud. Actually, these are the very vast assemblies of molecular gas and dust, and its mass is approximately 10 to the power 3 to 10 to the power 7 times the mass of the sun. And its diameter is basically 15 to 600 light years and composed of 90% of the helium and 90% of the hydrogen and 10% of the helium. Some of the taste elements, basically carbon, silicate materials, etc., also about 1% of the cloud mass. And next is the other type, that is the dark molecular clouds. These are diffuse filamentary clouds that are visible at high galactic latitude. And this the typical density range is 30 particles per cm cube. And these are the relatively local clouds where individual clouds range 0.1% and the masses ranges from 0.1 solar mass to 1000 solar mass. And this contributes 10% to 20% by mass to the molecular gas content in the local interstellar mass. And the small molecule clouds are basically block clouds. This is the we have said that these are the basically the simplest and isolated molecular clouds in Milky Way galaxy, and they are so thick that they are another technique, the magnitude of JHK,